Okay. Today we're talking about the cylindrical polar coordinate system. So the cylindrical polar coordinate system is a three-dimensional coordinate system. We're going to start with the two-dimensional version, or the two-dimensional version, which is the polar coordinates. Okay. Okay, so consider a particle of mass m moving in two-dimensional Euclidean space. So this is my sketch of this. The particle is going to trace some two-dimensional curve. This is my particle of mass m. I called it P. And say I have an origin located at some fixed point. What is this vector called from the origin to the particle P? What is it? R, right? It's the position vector to the particle. So that's R, the position vector to the particle. And previously we had defined the Cartesian basis, which I'm going to draw here. I'm going to take it to be this way, Ex and Ey. And remember the Cartesian basis, the Ex, Ey basis was a fixed basis. Very well. Now in polar coordinates, what we do is we're going to define a new basis, the ER E theta basis, and that's going to be a corotational basis. So the ER vector is going to move, is going to be located along R. So in Cartesians, we were able to write the position vector of the particle as x Ex plus y Ey. Now in polars, the position vector is along which polar unit vector? So I define ER to be along the position vector R. So my position vector in polars, expressed in polars is going to be along ER. Does that make sense? But ER is a unit vector. The length of that position vector, I'm going to call it R. So this is my vector. I have expressed it previously in terms of the Cartesians being x Ex plus y Ey. Right now I'm saying that it's a vector along ER. So what is the relationship between this scalar R and the scalars x and y?
The magnitude.
What do you mean?
So like in Cartesian it'd be this many x, this many y. Wow, y would be just downright straight up.
Yes, yeah. So what your friend is saying is that the length of this vector, the magnitude of my position vector, this is my position vector. Its magnitude, I can write it in two ways. The magnitude of R, I can write it in Cartesians. How can I express the magnitude of the vector R in Cartesians? Yes. What is it? Not quite, not quite. So, yes.
So like R times R?
R dot R, the square root of R dot R. Okay, that's the magnitude of the vector. And in Cartesians, r dot r is just x squared plus y squared, right? What about in polars? If I consider r dot r of this form of the vector, what will I get? Yes? Just r. So r is always a positive, so I do not need to put an absolute value here. Does that make sense? So this is a relationship I have now between the Cartesian coordinates x and y and r, which just says that r is the length of the position vector. Does that make sense? Okay. The next thing I'll do is I'll define the angle theta. So theta is an angle from Ex to R measured positive counterclockwise. So it's positive counterclockwise. So when I curl my fingers around EZ, that gives me the direction of increasing theta. Okay, great. So we have that angle theta, we have ER, and we have the basis EX anyway, the Cartesian basis. Very well. Okay, so EX, EY, and the angle theta. How can I express ER in terms of the Cartesian basis and theta? Again, so how can I express ER in terms of something along EX plus something along EY, in terms of its components along the Cartesian basis? Yes? Which is sine, which is which? Do you guys agree with your classmate? Raise your hand if you agree. You can take some time to. Okay, that's great. Yes. So basically, what's happening is that ER is this vector along EX plus this vector along EY, and this vector ER has length 1. The vector along EX has length cosine theta, and the vector along EY has length sine theta. Does that make sense? Any questions? Awesome. Okay. What we're also going to do is we're going to define another basis vector, E theta. So E theta is going to be perpendicular to ER, pointing in the direction of increasing theta. So E theta is perpendicular to ER. Okay, now take a minute, think about it. How can I write E theta in terms of the Cartesian basis? Take a minute, think about it. How can I write E theta in terms of the Cartesian basis? You can chat with your neighbor to make sure they have the correct answer. Raise your hand if you have an answer. So what is E theta? Can you write it down? What is it going to be? Okay, so any answers? What is E theta equal to? Okay, answers. No, no cross product. It's a simple projection like you did for ER. Yes, so before you answer, what is this angle here? Theta, right? Okay, so now what is the answer? Go ahead.
Negative cosine theta dx plus sine theta
Do we agree? Yes. Like this? Who agrees with this? Which one is it? Discuss, think about it. Which one is it? And why? We need to be able to get this systematically. Okay, so raise your hand if you think it's the first version. What about the second one? Okay, seems like we have a consensus. That's good. So yes, E theta has this component along EY, and that's equal to cosine theta. And this component along minus EX, and it's equal to sine theta. Okay? So it's the second. Eraser? Right. Okay, awesome. And then we can find the relationship between theta and x and y. So going back to the figure above, if I look at this triangle, what is the length of this side? Remember, the position vector has components x, ex plus y, ey. So what would the length of the horizontal and the vertical sides be? Right, x and y. So how can I write theta in terms of x and y? If I have a right triangle, angle theta, length x, length y. This has length r, which is the hypotenuse, which is x squared plus y squared. So how can I write theta in terms of x and y? Yes. Right. Tangent angle theta is y over x. Right. So these two equations here are two equations, a system of two equations for the two unknowns. If I have x and y, I can find r and theta. And if I have r and theta, I can also find x and y. Okay? Any questions so far? Raise your hand if this is kind of making sense. Okay, cool. Yes. Yes, ER and E theta are also unit vectors.
But will they be unit vectors? Because like if we like take angle theta as 45 degrees, right? Will be the sine and cosine will be 1 divided by square root of 2, and then the length of. Okay, no.
No, that's a great question. Actually, let us verify. If I take, for example, ER, and I calculate the magnitude of it, the magnitude of ER, what is the magnitude of ER equal to? Yes. No. Yes. 1. Why? Exactly. So that's the square root of ER dot ER. So ER dot ER, I'll take the x component squared and the y component squared because the EX or EY components are going to cancel out. So that's the square root of cosine squared theta plus sine squared theta, which is always equal to the square root of 1, which is 1. Okay? So and the same applies for E theta. These are unit vectors. As long as EX and EY are unit vectors, which they are. Okay? Any other questions? Awesome. So let's go back to our kinematics. We said that the position vector is equal to RER. So again, our original setup was that there was a particle that's moving in the plane that's tracing a specific curve. We wrote the position vector of the particle and we defined the polar basis and we express its position vector as RER. Now I want to calculate the velocity and the acceleration of the particle. So let's start by calculating the velocity. How do I calculate V? Yes. Exactly. V is dr by dt. dr by dt, we also wrote that as r dot, which is the derivative of r er, right? Now let us think. Does r change in time? And does er change in time as the particle is tracing the random curve in 2 dimensions? What is it? The magnitude of the position vector. Think about it. Think about a point tracing a random curve in 2 dimensions. Is the magnitude of the position vector always going to be the same? Necessarily? No. So r, the magnitude of the position vector, r scalar, not fixed. It changes with time. Does er change in time? Yeah. Also. So again, we have the particle moving in 2D on a specific curve, tracing a specific curve. Say initially it's located here. This is my r. This is my ER pointing along r, and this is my E theta. Whereas at a different time, the particle is here. This is my position vector. This is my ER, and this is my E theta. So r scalar and ER vector are both changing in time. Does that make sense? So when I take this derivative, I'm going to have to use which rule? Not the chain rule, the product rule, the derivative of a product. That's going to be r dot er plus r er dot, right? Very well. Now, r dot er plus er dot, we have an expression for er. Let us try to see if we can simplify this. So er is cosine theta ex. I'm copying the expression from the other board, plus sine theta ey. Can you calculate the derivative of er? Please go ahead and do it. Write it down, the derivative of er. So think about it. Take the derivative of cosine theta. Is theta a function of time? Does theta change in time? Yes, it does. Okay. But Ex and Ey are fixed. So how do I take the derivative of Er? So here I'm going to use the chain rule. I'm taking the derivative of a function that depends on time. So cosine theta and theta depends on time. What's the derivative of that going to be? What's the derivative of cosine? Negative sign. And then I have to use the chain rule. I have to multiply by the derivative of theta. So that's going to be minus sine theta times what? Theta dot, right? G of f of x prime is g prime of f of x, f prime of x. That's the chain rule. The derivative of the function times the derivative of what's inside. So here my g of x is cosine x and my f of x is basically theta of x being time. And the x is constant. What's the derivative of the second term? Do we agree with this? Raise your hand if you do. Okay, awesome. So that's Er dot. So it's theta dot into minus sine theta Ex plus cosine theta Ey. Okay. Does anyone recognize this unit vector here? It is a unit vector, right? What is it? E theta. Very good. So Er dot is theta dot E theta. So, okay, that's great. That's noteworthy. Er dot is theta dot E theta. Is Er dot a unit vector? No. Right? It's not a unit vector. What is the magnitude of Er dot? No, it's not a unit vector. A bit more precise? Yes. Exactly. Okay, chat with your neighbor, make sure they understand this. Are we all good? Any questions? Awesome. So Er dot is the magnitude of theta dot. So the derivative of a vector has to do with a change in two things. The change in its magnitude. So Er is a unit vector. Its magnitude is not going to change. So there's no component due to that. But it also has to do, the derivative of a vector also has to do with a change in its direction. And the change in its direction is equal to theta dot E theta. Okay, so again, the derivative of a vector, and we're going to see this more clearly later in the semester, has to do with two things. The derivative of a vector has to do with the change in its magnitude in time and the change in its direction in time. So as a particle is tracing a curve, let me draw this. As a particle is tracing a curve, this is my Er at time t. This is my Er at time t plus dt, and this is my Er. This is my E theta. So in textbooks, they do this calculation. They show this kind of using geometry or graphically. They'll take the difference between these two vectors and they'll observe that it points along E theta. Okay. Second thing, what is the derivative of E theta? since we're calculating the derivatives of unit vectors, E theta dot okay, do it yourselves, please, and you feel free to chat with your neighbors if you need to check your answer. Yes.
Minus theta dot x ER.
Correct. Raise your hand if you're done. Okay, I'll wait for one more minute. Okay, great. We're all done? Questions? Okay. So going back to our expression for the velocity v was equal to r dot er plus r times er dot, but I'm going to replace er dot by what we found it to be, theta dot e theta. And this is the expression of the velocity of a particle expressed in polars. Are we okay with this? Remember in Cartesians, the expression for the velocity was x dot ex plus y dot ey. Now, if I wanted to calculate the acceleration of the, or the expression of the acceleration of the particle expressed in polar coordinates, what would I do? dv by dt, exactly. So that's going to be our exercise for the day, to be done individually. So please put all your electronics aside, grab a pen, and this time you do not need to submit to Gradescope. We'll do the submitting from now on. But make sure you write your full name and your student ID on the top. So it's a quick 15-minute exercise. Please take a paper and pen.
What do you say at the end? It's not going to submit it to Gradescope now.
Yeah, do not submit the papers to Gradescope. I'm going to collect them at the end, and we'll submit them for you. No papers? There you go. Okay, does anyone have a paper? Awesome. Can I put this in your bag, please? Thanks. Do you need your electronics right now?
Yeah, I just charging my iPad, that's all.
Okay. And we're going to put this away. And turn the iPad off. Can you put your phone away, please? Thanks. Phone's away. Phone away. Can you put your phone away, please? Also
the is the fact that this is bolded like the same as just saying this?
Yes.
Okay.
Thank you. Okay, do I have all the quizzes? Need them, please? Please submit all your quizzes and open up set 5, problem 1. The rocket is fired vertically and tracked by the radar station shown. So there's the radar station and the rocket is going in rectilinear motion. When theta reaches 60 degrees, other corresponding measurements give the values are. So when theta is 60 degrees, we have r is 9 kilometers, our double dot is 21 meters per second squared, and theta dot is 0.02 radians per second. Okay, so these are the measurements from the radar. When theta is 60 degrees, I have the value for r double dot, and theta dot. And I need to calculate the magnitudes of the velocity and acceleration of the rockets at this position. And what do I know about the motion of the rocket? What kind of path is it tracing? Yeah, it's a straight line, so it's like linear motion, basically. Okay, so what do I do? Any ideas? How though? How? How?
It's r cosine theta and is r sine theta.
Right. Any other ideas? Yes. Anything.
I think you could write out in Cartesian the coordinates for the position and then use the transformation.
Okay. So what your friend is suggesting is using both Cartesian and polar coordinates. So I'm going to write my position vector, and also I'll do my velocity and acceleration vectors written both in polars and Cartesians. So r in polar is r er, and in Cartesian it's x ex plus y ey. Okay, and let us draw our bases. So if I want to draw my Cartesian basis, let me draw it like this. Ex and ey. How would I draw my polar basis? Where should er point? Show me with your fingers. Right, along r. And what about e theta? Perpendicular which way? This way or that way? E theta. Always be careful that ex plus ey, that should be equal to er plus e theta. So the two systems, they have the same handedness. Ex cross ey pointing outside the page, then er cross e theta also needs to point outside the page. Does that make sense? Okay. So, okay, this is our basis. Let me see, and then which out of these x and y? So we know that one of them is going to be constant because we're going in rectilinear motion. Which one is constant? Is it the x value or the y value of the position vector of the rocket? The x value. That's a constant. Okay. Let me see what I already have. I have that r is 9 kilometers, which is 9,000 meters, and I can express er in terms of the Cartesian basis. Cosine theta ex plus sine theta ey. And theta is given, right? It's 60 degrees. It's CEX plus YEY. So can I figure out what C is?
Yes.
How? What is C? Yes? Exactly. I'll project this equation along ER, dot with EX, and I'll get 9,000 cosine 60 degrees is equal to C. That's my C. And dot EY, I'll get 9,000 sine 60 degrees is equal to what? Any questions? Yes.
Just want to clarify that EX and EY, they are unit vectors and they're magnitude of each one, right?
Yes. Okay. Let's do the same thing for the velocity. But for the velocities, I'm not going to replace numbers. I'm going to use the variables, r, theta, and so on, so that the expressions I get, they're going to be valid for any configuration for any angle theta. So V, what is it in polars? R theta dot E theta. And Cartesians, that's x dot EX plus y dot EY. Okay. Let's see. If I want to project this equation along EX, what will I get? Oh, before I do that, what is x dot equal to? 0. That's just 0. Why? Because x is constant, right? So that's 0. So my velocity is just y dot EY. Okay. So what are my unknowns in this equation? R dot ER plus R theta dot E theta equals y dot EY. Do I know R dot? Do I know R dot? No. R dot is an unknown. ER, do I know ER? Do I know where it points? Yes, because I have the angle theta, I know where ER points. The same for E theta. And R, I also know it's 9,000 kilometers. What about theta dot? Do I know it? What do I not know? Y dot. Okay, so this is an equation. It's an equation in 2 dimensions, and it has 2 unknowns. Can I solve for the 2 unknowns? 2 scalar unknowns with 1 vector equation in 2D? What? How many scalar equations can I get out of this vector equation? 2, right? I can get 2 scalar equations by projecting it along ER and E theta or along EX and EY, any 2 independent vectors in the plane. So I can get 2 scalar equations out of this 1 vector equation. So can I then solve for the 2 unknowns? Yes or no? Yeah, I can solve for the 2 unknowns actually. So say I want to solve for R dot. I want to solve for R dot and I want to get rid of the other unknown. Is there some smart projection I can take to solve for R dot in one go? So I want to solve for R dot and I don't want the other unknown to show up in my equation. Is there some smart projection I can take to do that? Because for example, if I project along ER, AY dot ER is not 0. That's going to be a non-zero term. So let us see. Your friend is suggesting, let me project this equation along EX. If I project along EX, I will get, will this term go away? Yeah, because I'll have AY dot EX. So that's going to be equal to 0. Now what about the other ones? I'll have R dot ER dot EX plus R theta dot E theta dot EX. Interesting. So remember ER is cosine theta EX plus sine theta EY. And E theta is minus sine theta EX plus cosine theta EY. So what is ER dotted with EX? That's ER. What is ER dot EX? Is it cosine theta? Raise your hand if you agree. Okay, is it something else? So think about it. Chat with your neighbors. What is the answer? ER dot EX. So what you can do to calculate that is take every term of this equation and dot it with EX. So ER dot EX is cosine theta EX dot EX is what? 1, right? Plus sine theta EX dot EY. What is EX dot EY? 0. So what am I left with? ER dot EX is equal to what? Cosine theta. This is very important. Do we all understand this? Raise your hand if you do. Great. Questions? Anyone? Questions? So then, what is E theta dot EX? I need a consensus on this one. E theta dot EX. This is E theta here. Yeah, raise your hand if you know the answer. E theta dot EX. Okay. What about the rest of us? So make sure your neighbor knows the answer. If they don't, convince them. What is it going to be? Minus sine theta. Do we agree it's minus sine theta? So again, it's a very systematic procedure. I'm taking this equation and I'm dotting E theta dot EX is equal to minus sine theta EX dot EX plus cosine theta EY dot EX. That's 1 and that's 0. Very systematic, I'll get a minus sine theta. Okay, that's very important. So I have R dot. I'll be organized and I'll go under this. R dot cosine theta minus R theta dot sine theta is equal to 0 and I can solve for R dot. Cool. I found my first unknown, that is R dot. Now, say I wanted to find Y dot first. Which smart projection could I have taken to find Y dot without depending on R dot? So again, the question is, say I wanted to find Y dot first, which smart projection can I take to find Y dot so that my expression will not depend on R dot? Think about it. I want to solve for Y dot without depending on R dot. Raise your hand if you have the answer. Great. What is it? E theta. So if I project along E theta, will it get rid of this term? Yes. Great. So I'll project along E theta. And I'll say that R dot ER dot E theta that's 0 plus R theta dot is equal to Y dot EY dot E theta. Did I make any mistakes? And what is EY dot E theta? EY dot E theta cosine theta. That's great. So Y dot is equal to R theta dot over cosine theta. Okay. That's great. So we need to get used to these projections. They are very important. Maybe they don't seem as important right now because you could have solved the problem a different way, but in a few weeks they will be very important. Okay? So let's get used to projections now. Okay, this problem is not done yet. You still need to find acceleration components, but I'll let you do it on your own at home or during this exercise section. I have a recording, a video solution of this that is linked in the course website, a video solution of this problem. Let us do another example. The simple pendulum. So this problem just involved kinematics, so motion, no forces. We're going to do the other example of a simple pendulum, and we're going to use Newton's second law, F equals ma, which you learned about last time. So we're going to use some kinetics. And for that, our steps are always going to be, we're going to set up our origin and on our basis. Steps, these are important. For solving a kinetics problem, we're going to set up our origin, our basis, set up origin, basis, and the vectors R, V, and A. Step 2, we're going to draw our FPD. Step 3, we're going to write the vector equation of the balance law. The balance of linear momentum is what we learned so far. And step 4, we're going to do our analysis. These are very important. You've probably seen in quiz 2 that if you didn't follow these 4 steps, especially if you didn't write the vector equation of the balance law before you projected, then you lost points. And that's going to happen. You're going to lose more points in the exams if you don't do that. Write the vector equations of the balance law. F equals ma, the expression for all the forces, the expression for all the accelerations, and then for the acceleration, and then you can project. Let's do this. So consider a simple pendulum. Consider a mass m suspended by an extensible massless string of length l. Okay. Consider a mass m, or a particle of mass m, suspended from a fixed point by a massless inextensible string of length L. And this is our figure. This is the particle of mass m, and I have my gravity pointing down. The question is, find the equation of motion of the mass m. And I'm going to give us a basis here. I'm choosing my origin to be this fixed point. Origin is always a fixed point. So this is my position vector to the particle. So if I want to draw my ER unit vector, in which direction would ER point? Show me with your fingers. Yes, along the string ER. Now, if theta would point, depending on how I take my fixed basis, so if I take EX like this, EY like this, so different from our usual, EX is pointing down, vertically down, and EY is pointing horizontally to the right, then what is the angle theta? It's this angle, right? Measured from Ex. Then what is the direction of theta, E theta? The vector E theta, does it point this way or that way? Up. Why up? Yes? Because of the right hand rule, right? So Ex cross Ey should be equal to Er cross E theta. That's very important. Does that make sense? So Ex cross Ey points outside the page. Er cross E theta points outside the page also. Okay, so we've done step 1. No, not yet. We still need to express the position vector and the velocity vector in terms of our chosen basis. Which vector, or in which basis do you think it would be easier to express the position vector of the particle? In polar. Why? But why really? Is it more, or is it easier to express the position vector of a particle, of this particle in polars? Let me ask you the question differently. How many degrees of freedom does this particle have? So in general, for a particle moving in a plane, how many degrees of freedom? If it's unconstrained, no constraints, how many degrees of freedom does a particle moving in 2D have? 2 degrees of freedom. If I know its x and y coordinates, I can locate the particle. Now here, this particle is constrained, right? What is the constraint that this particle is subject to? Yes. What about R? Yes, R is constrained. Exactly. The particle is at a certain fixed length from the point, the origin O. So the position vector, its length, is constrained. So how many degrees of freedom does this particle now have? It's a general unconstrained particle in 2D has 2 degrees of freedom, but we've added one scalar constraint. So how many degrees of freedom does this particle have left? 1, which is the angle theta. So if I wanted to find the equations of motion of a particle, all I need to do is to find how many equations? One equation for theta. It's going to be a differential equation in theta that once you solve, you will get theta as a function of time. And if you know theta as a function of time, you figured out the motion of this whole system. Okay? Now the position vector, I can express it in 2 ways. R, ER in polars, and then X, EX plus Y, EY in Cartesians. But I have this additional constraint that in polars I can express it as what? How can I express the constraint that the magnitude of the position vector R is constant? How can I express that in polars? R dot is equal to 0. R is equal to a constant, basically, right? So R is equal to L. Whereas in Cartesians, I'll have to express that in a little bit more complicated way, which is that x squared plus y squared is equal to L. So from this, it just seems more easy to use the polar coordinates. So I'm going to say R is L ER. L is a constant. So if I wanted to write my position my velocity vector V, R dot ER plus R theta dot E theta. In this particular problem, what is R dot equal to? 0. Why? Because R is equal to L. So my velocity vector is just L theta dot E theta. Okay? And my acceleration vector in general is R double dot, this is what you derived just now, minus R theta dot squared ER plus R theta double dot plus 2R dot theta dot E theta. So how many terms are going to disappear because of this constraint? 2, right? All the terms that have derivatives in R. This is 0 and this is 0. So I'm left with A is equal to minus L theta dot squared ER plus L theta double dot E theta. Any questions? Yes. It's just that this mass m is suspended by a string. So there's a string between O and m, and that string is inextensible. So that distance, which happens to be the length of the position vector, which is r, that this is equal to a constant, which is the length of the string. Okay? In the homework problem, you're going to have homework 2. So you have homework 1, and homework 1 is due when? On Friday. Homework 2 is already posted, or I'm going to post it after lecture. I'll double check. That's going to be due next Thursday. And for that, you're going to animate the motion of a spring pendulum. So the pendulum is not going to be extended by an extensible string. It's going to be extended by a spring that can extend and compress. So that's going to be your homework. You're going to solve the motion. So get the equations of motion, solve them, and then animate the motion. And there's a video that's going to help you animate the motion. So the video I have is animates the motion of a simple pendulum, and then you're going to kind of change it to animate the motion of a spring pendulum. When you're submitting your homework on Gradescope, please make sure, when you're submitting anything on Gradescope, please make sure you select the questions. So if we say part 1, part 2, part 3, make sure you select the questions. If you do not know what I mean, please let me know. Send me an email. Or pass by office hours. Okay. So that was step 1. We've written our position, velocity, and acceleration vector, our origin, our bases. Okay, step 2. Let us draw the free body diagram of the particle. How many forces are acting on the particle? Raise your hand for 1. Raise your hand for 2. Raise your hand for 3. What are the 2 forces? What are they? Weight, the weight force, and the tension. In which direction does the tension act? Along the string. So the tension force. So notice that every time you have a constraint, the constraint here being that R is equal to L, you're going to have an associated constraint force. That's going to be here the tension force. For example, when I'm standing on the ground, I'm subject to the constraint that I cannot penetrate the ground. My position vector needs to be greater, or my height needs to be greater than the height of the ground. So I'm going to be subject to the constraint that is the constraint force, that is the normal force from the ground on me that's going to enforce this constraint. And the same thing happens here. We have the constraint that the length of the string is constant, and that's going to be enforced by the constraint tension force T. Okay, so the weight is along which direction? Which unit vector? mg(ex). What about the tension force? Er or minus Er. Here the tension force is T is positive scalar. And the tension force along minus Er. So strings can only sustain tension, they cannot sustain compression. Deal? Questions? Okay. What do we do next? The vector equation for the balance law, the balance of linear momentum. F is equal to ma, and I'm going to write all the forces. mg(ex) minus t er is equal to m. A is minus L. Very well. Any questions? That's a very important equation. It's important to get to this point. How many unknowns does this equation have? What are my unknowns? M is a given mass, G is a given value of gravity, these are known. What about T? The tension force is an unknown. What else? L is a given length. What else? Theta. Theta dot, theta double dot, all of these are unknowns. I'm going to consider them to be one unknown. Theta is a function of time. And if I know theta is a function of time, then I can figure out its derivative, theta dot and theta double dot, right? So two unknowns, one vector equation in the plane for two unknowns. Can I solve for the two unknowns? Raise your hand for yes. Raise your hand for no. Yes, you can solve for the two unknowns. If I want to solve for the tension force, along which direction should I take my projection? Well, let me ask the other question first. If I want to get a differential equation for theta without relying on the tension force, what do? I want to get a differential equation for theta. I do not want it to involve the other unknown, that is the tension force. Along which direction should I take my projection? E theta, right. If I project along E theta, will I get rid of this term? Yes. So I'll do mg Ex dot E theta is equal to m. Er dot E theta is 0, and I'm going to get L theta double dot E theta dot E theta is 1. Right? What is Ex dot E theta? And because of the setup I've taken, these equations up there, the expressions for Er and E theta in terms of Ex and Ey, they still apply. Because I've taken basically the same setup. Er and E theta being rotated, Ex and Ey rotated by an angle theta. So what is Ex dot E theta? Ex dot E theta. What is it? Negative sine theta. Raise your hand if you agree. Good. So I'll divide by mass, and I'll take everything to one side, and I'll rearrange this equation to become theta double dot plus G over L sine theta is equal to 0. Raise your hand if you've seen this equation before. Maybe x double dot plus omega n squared sine theta is equal to 0. No? Okay, interesting. You should have probably seen this in a physics course. Well, maybe you took the small angle approximation. Do you remember that? If theta is small, how does this equation simplify? If theta is small, then sine theta is approximately equal to what? Theta. And then you get theta double dot plus G over L theta is equal to 0. And this equation you can easily solve by hand. This equation is a little bit more complicated to solve. It is more complicated to solve, but you can solve it numerically in Python or MATLAB, or you can write your own code to solve this, like you're going to do for homework 1 and homework 2. Okay? Does that make sense? Any questions? So that's going to be my differential equation for the motion. That's going to work for any theta. What about my tension force T? If I want to solve for that, what do I do? If I want to solve for the tension force T, I can take any projection as long as it's not along which direction? E theta. If I project along E theta like I did, I'll get rid of T. So if I take any other projection along Ex, Ey, or ER, I'll get an expression for T. So if I project along ER, mg Ex, what is Ex dot ER? Cosine theta minus T is equal to m minus L theta dot squared. So that's my expression for the tension force T is equal to mg cosine theta plus ml theta dot squared. So once you've solved your differential equation, found theta as a function of time, then you can plug in and find tension force. The tension force is not going to be constant; it's going to vary in terms of time. And it will be interesting to see where it's max, when it's min, and so on. Any questions? Questions? Great. Before we move on to another topic, I want to discuss the expression of the acceleration that you derived. So let me do that here. Let me make sure that my mic is working. Oops, it's dying. Let's change the batteries. I think we're fully charged now. Okay, so we still have, 45 minutes left? Time flies. Okay, so we're gonna look at the expression for the acceleration a little bit, and then we're gonna explain constraint motion, so pulleys and stuff. Okay, so let's start. The expression for the acceleration, A is r double dot minus r theta dot squared er plus r theta double dot plus 2r dot theta dot e theta. Actually, shall we take a 5-minute break before we continue? Go 5 minutes and come back, and you have to go take a small walk and come back. 5 minutes till 11:50. Yeah. Yeah, this is it. This is done. We found the equation of motion and the expression for the t. That was an example that I just gave you. Not from these sets. Okay. Go everyone. Stretch your legs a little bit, then come back. think our 5 minutes are up. Okay, so this is the expression of the acceleration you derive, and we have names for all these terms: the radial component, the centripetal component, the tangential, and the Coriolis component. So let's think a little bit about what these terms mean. We're going to try to get a small intuition of what they mean. Okay, so can you think of a situation where we only have the radial term of the acceleration? So if we only have this term, then and all the other terms need to be 0, then what is theta? So again, A is equal to r double dot ER is just, the acceleration is purely radial. What does theta need to be for this to happen? So what are all the other terms? Zeros, right? Zeros. If the acceleration is just r double dot ER, the other terms are zeros. So this means that theta dot and theta double dot is 0, because r is non-zero. R is different than 0, r dot is different than 0. So we'll need that theta dot is equal to 0 and theta double dot is equal to 0. So theta is just a constant. So what kind of motion is that? If theta is a constant, theta dot and theta double dot are 0, and the acceleration is just radial. So what kind of motion is that? Theta is constant. So I have Ex, I have Ey, I have my position vector to the particle, and theta is constant, and the length of the position vector is allowed to increase and decrease. What kind of motion is that? Rectilinear motion, right. It's a motion along the straight line. Let's think of that. So if I have, for example, this system, a mass suspended by a pendulum vertically, and the pendulum is going up and down like that, that's my motion, then the acceleration is purely radial. So the radial acceleration has to do with the change in the magnitude of the position vector. Does that make sense? Radial acceleration related to change in magnitude of the position vector. Okay. Now let us look at the centripetal acceleration. Is there a case where the acceleration is purely centripetal? So I would need r double dot to be equal to 0, r theta double dot to be equal to 0, to r dot theta dot to be equal to 0, but minus r theta dot squared, that should be different than 0. Any ideas of a motion that could satisfy all this? Yes?
Particle moving in a circle at constant velocity.
Yes, let us think about this. If I have a particle that is moving on a circle, and this is my origin, and this is my particle tracing a circle, not my best drawing, so be better than me, please. R, and this is my ER, E theta, say EX, and so if a particle is moving on a circle, then r is what? Is it changing in time? No, it's constant. So these two terms are going to be equal to 0, because r dot is 0 and r double dot is 0. R is equal to a constant, r dot is 0, and r double dot is 0. And this term is going to be non-zero. R is a constant. And additionally, to have this term to be 0, we're going to need theta double dot to be 0. theta double dot to be 0, meaning that theta dot is equal to a constant. So now I can write my velocity as being r dot er plus r theta dot e theta. This we've already established is 0, and r and theta dot are both constants. So the magnitude of my velocity, that's going to be a constant. So for a motion like that, the acceleration is purely centripetal. So in which direction does it point? Along minus er. So this is my acceleration. So I actually need a force to sustain this acceleration, which is going to be a force from the rail. Maybe if I have a particle moving on a circular rail, there's going to be a force that's going to sustain this motion. I think about it this way. If I had a cord and I had a mass suspended at the end of the cord, and I was holding the cord and I was turning like this, the mass would trace a circle, right? And I would need to be pulling on the cord to be able to constrain that motion to happen. If I release the cord, the mass is not going to go on a circle anymore. So there is a force in that cord along ER that has to balance the centripetal acceleration. Okay? So that's the case where the acceleration is purely centripetal. So hopefully that gives you a bit of intuition of what the centripetal acceleration is. Okay? Let's take the other case where we have tangential acceleration. So the acceleration is tangential. A is equal to r theta double dot e theta. Is that motion possible where the acceleration is purely tangential? Let us see. So I'll need r double dot to be 0. I'll need r theta dot squared to be 0. And I'll need 2 r dot theta dot to be 0. I'm not sure if that's going to be possible. Because, let us see. This means that r dot is equal to a constant. R dot is equal to a constant, but theta dot needs to be equal, not be equal to 0. That's not going to work out. I think at least we're going to have the minus r theta dot squared er term. Okay. So that's not possible. The acceleration cannot be purely tangential. At least we're going to have that term, the centripetal term. We can think of a motion that satisfies this. It would be the same system as this one, a particle moving on a circle, but right now its velocity, its speed is not going to be constant. So it's going to be pushed around the circle so that its speed increases or decreases. So that's that motion. That pushing the particle tangentially around the circle to increase or decrease the acceleration, that gives us the tangential component of the acceleration. Does that make sense a little bit? So the tangential acceleration does have to do with the change in the magnitude of the velocity, whereas the centripetal acceleration had to do with the change in the direction of the velocity. Remember, in this previous case, the magnitude of the velocity was constant, but the acceleration was still non-zero because the centripetal acceleration had to do with the change in the direction of the velocity related to change in velocity direction. components is related to the change. I mean, these are kind of rough observations, intuitions, but it's an intuition that works a lot of the times. This has to do with the change in velocity magnitude. But of course, it's also related to theta dot, which is the change in the direction of the velocity. Yes?
So am I right by saying that radial component is like change of velocity in like ER?
Yeah.
And the tangential is change of velocity in theta?
Yes, but then you have the additional terms, the centripetal and the Coriolis term. Now, the Coriolis term is named after a person, Coriolis. And it has to do with the fact that the frame is rotating. So the Coriolis acceleration, we cannot have it on its own. The least we can have is also the minus r theta dot squared dr term. But just by its composition, it depends on r dot and theta dot. It depends on theta dot. It has to do with the effect of the rotating frame. We're going to talk more about the Coriolis acceleration when we get to rigid bodies. So I'm going to pause this for now, and we're going to talk more about this later. Any questions? We still need to talk about the cylindrical coordinate system, the cylindrical polar coordinate system, which is an extension of the polars to 3D. So in the last 2 hours, what have we done? We've introduced a new basis, the polar coordinate system, for a particle moving in 2 dimensions. We've derived the velocity and the acceleration vector of the particle in this basis, and we did a few examples. Kinematics example, a kinetics example, and we talked a little bit about the acceleration expression, its components. Now we're going to consider the same particle moving in 3 dimensions. So consider a particle moving in 3 dimensions. So that particle is going to trace a random curve in 3D. Still, I'm going to draw the position vector to the particle. I'm going to call it R. And I'm going to draw my Cartesian basis, EZ. And then in the plane, EX and EY. Are you with me so far? Okay. So this is tricky and it gets students confused a lot. For the cylindrical coordinate system, ER does not point along R. This is not correct. ER does not point along R. For the cylindrical coordinate system, we have to project R in the EX, EY plane. We project R in the EX, EY plane, and ER points along the projection of R in the EX, EY plane. So ER, be careful, attention, ER points along the projection of R in the EUX, EY plane. And E theta, I'll define the angle theta the same way as I did in polars, and E theta is also defined in the same way. So ER and E theta are defined in the EX, EY plane. Exactly like they did, they were defined for the polar coordinates. ER is cosine theta EX plus sine theta EY. And E theta is minus sine theta EX plus cosine theta EY. So again, if I look in the XY plane, I'll have EX, EY, and then if I look in the XY plane, I have EX, EY, and ER, E theta, and ER, E theta are a rotation of EX, EY by an angle theta. Okay? But I'll give you a minute. My position vector in cylindrical coordinates, it has a horizontal component in the plane, RER, plus it has another component along which direction, can anyone guess? So that position vector R, I can write it as RER in the plane, this yellow vector here. That one is RER in the plane, plus another component along which direction is that vertical component? Along EZ, and I'm gonna call its length Z. Okay, so this is my position vector in cylindrical coordinates. It's the polar component in the EX, EY plane, which is the projection of the position vector along the horizontal, plus the vertical, Z, EZ. So it's basically the polar plus you add the Z component, the height. Okay? And then the velocity and acceleration vectors are defined in the same way by taking the derivative of R and V respectively, but then we have to add the Z dot EZ component and the Z double dot EZ component. So R dot ER plus R theta dot E theta plus what? Z dot EZ. And this one is R double dot minus R theta dot squared ER plus R theta double dot plus 2 R dot theta dot E theta plus what? Z double dot EZ. Okay? And this is sometimes this can get confusing for students. Let me take an example. Particle on cone. I have a particle on a cone, like this. And this is my origin. I'll take EC to be up, and EX, and EY. How do I draw my polar basis, my cylindrical basis, sorry? First, I'll draw my position vector from the origin to the particle. So where does the position vector point? How does it point? That way, right? From the origin to the particle. Raise your hand if you agree. Awesome. Now, how does ER point? Show me with your fingers. Great, great. So this way, right? This way. Not that way, not along ER, because we're not doing polars anymore. It's that way. It's that way. It's along the horizontal projection of the position vector R. And this vector is what? EZ. And where does E theta point? Remember, it needs to complete ER cross E theta is equal to Ez. So we need the right-handed basis to be complete. ER E theta Ez, the cylindrical basis is right-handed. So ER cross E theta is Ez. What is E theta equal to from in terms of cross products of the other unit vectors? E theta is equal to what? Ez cross ER. Do we all see that? Ez cross ER is E theta. So if I do Ez cross ER, is that going to be into the page or out of the page? Into the page, right? So here, this is my vector, E theta, and that's simple. What does it mean? That it's pointing into the page, right? This symbol means what? That it's pointing out of the page. Okay, wait. So this is my cylindrical polar basis in this problem. Okay, let's do another example of just drawing a basis. Let's do it here. Say I have a particle in a tube, and the tube is rotating. So I have a particle in a tube, and the tube is rotating. And I have my origin here. And the particle is inside the tube. How do I draw my cylindrical basis? This is my position vector to the particle. How does Ez point? Yes, that's another important point we need to make. That is Ez a fixed vector or a moving vector? Ez, is it fixed or moving? Fixed. But ER and E theta are what? Moving. So notice in this problem, as the particle moves along the surface of the cone, does Ez change? No, but ER and E theta, they're following the particle always, so they're moving. So whenever we have an axis of rotation, the axis of rotation is fixed, and Ez points along the axis of rotation for the polar basis. So for here, Ez points along the axis of rotation like this. So where does ER point? Right, along the horizontal projection of R. So ER pointing like this outside the tube. And then E theta, same as the previous problem, is going to point inside the page. Now, if the particle is now, if the tube is this way and the particle is now here, where does ER point? That way. That's my position vector. Where does E theta point? Out of the page. Ez always the same, vertically up. Double check, ER cross E theta. Well, I think we have something wrong. So we said that E theta is Ez cross ER. Oh, so it's out of the page. Okay, let us see now. ER cross E theta, which is outside of the page, is equal to Ez. Okay, that makes sense. Or you can think about it this way. ER, E theta, Ez. That's the right-handed basis. Makes sense? Yes.
So you said ER and E theta follow the particles around, like in its
Yes.
Is EZ also like translated to its position or no?
You can translate it. If you translate a vector that doesn't change it, it's still fixed. But its direction will not change. The direction of ER and E theta will change. Okay? So maybe what I'll do is I already have a few animations of a particle moving on a random curve with the vectors changing. So I'll post these animations so I can see them. I'll post them on the website. Keep an eye out for them. Any other questions? I think these are happy with visualize. And then homework 3, we're going to have a random curve, a helix, and we're going to draw the Cartesian basis on it, the polar basis on it, and we're going to add another basis, the Serifine basis on it. Okay. Other questions? Okay. One last thing, constraint motion. Okay, so we started discussing this a little bit when we talked about the degrees of freedom of a system. The degrees of freedom of a system is the minimum number of coordinates we need to describe the motion of the system. So, degrees of freedom Okay, so for example, if I have a general particle moving in 3 dimensions, for a particle moving in E3, how many DOFs, the degrees of freedom, does the particle moving in 3 dimensions have? 3, right? 3 degrees of freedom. I need 3 coordinates, x, y, and z, for example, to describe the location and the motion of the particle. Now, if I have 2 particles moving in E3, for 2 particles moving in E3, how many degrees of freedom do the 2 particles combined have? 6 degrees of freedom, right? So each one has 3 degrees of freedom. In total, both of them, they have 6 degrees of freedom. So I need 6 coordinates, x1, y1, z1, and x2, y2, z2, to find the motion or to locate both particles. Now, if I add a constraint to those particles, maybe I connect the particles when moving in E3 by a rigid rod. So 2 particles in E3 connected by a rigid rod. Now, how many degrees of freedom does my system have? No. So I started with 6 degrees of freedom. I added how many scalar constraints? One constraint, which is the length. The length between them is constant. The distance between them is constant. So basically that x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z2 squared is equal to L, the length of the chord. So I added 1 scalar constraint, which that is the mathematical equivalent of connecting the 2 rods by the 2 particles by 1 rod. So I added 1 constraint. So how many degrees of freedom do I still have? 5. 6 minus 1 is 5. So when I add constraints, I decrease the number of degrees of freedom. When I add constraints, the number of degrees of freedom or the degrees of freedom decrease. And they are replaced by constraint forces. So, for example, when I connected the 2 rods to the 2 particles by a rod, I added a constraint. I added an equation to the system, but this constraint also adds an unknown, that is an unknown tension force that's now happening between the 2 rods that I need to find. Okay? Oftentimes, expressing or writing this constraint will help us solve for the motion of the system. Let me think of an example. I have a pulley, and I have two masses A and B connected by the pulley. And A and B, they're only moving down. So this is a massless pulley. And A and B are just moving up and down. So how many degrees of freedom does this system have?
1.
A and B. 1. What do you mean? Who said 1? Yes, why?
Because they have the string will be always the same length and they move up and down.
Right, right. So what your friend is saying is that if I know the position of A, if I know the height of A, one coordinate, the height of A, do I know the location of B? The location of B is fixed. Why? Because the length of this chord is constant. And if A goes down a certain length, what's going to happen to B? It's going to go up the same length. Okay? Now we can express this constraint, especially having to do with pulley systems, in terms of something called the chord equation. So for pulley systems, we can write the chord equation to express the constraints. So let's do that for this system, which is pretty easy, but that's going to help us a lot when we're looking at more complicated systems, like the ones you have in set 6, where you have, for example, multiple pulleys. And you have, masses connected by multiple pulleys, maybe like this. Okay, so the formulation we're going to do right now is going to apply to systems like this that are more complicated, connected by multiple pulleys. Okay, so the steps are, you're going to take a datum, choose a datum. Sometimes you might choose multiple datums, but what is important about the datum is that it's fixed. And you can locate the particles, the masses, relative to the datum. So this is my SA, this is my SB, the particle relative to the datum. And 3, we're going to write the chord equation. Which is this. The chord equation says that if I add up the lengths of SA, this length, plus the lengths of SB, plus whatever constant length this is, I'm going to get what? So if I add up this length, SA, this length, SB, and whatever constant length this is, what do I get? The length of the string, which is another constant. Okay? And I can differentiate the chord equation to get relationships between SA and SB. So I can get that S dot A plus S dot B is equal to 0, meaning that whatever A goes up, SB is going to go down. S dot A is minus S dot B. And the same for the acceleration. And that will help us solve for the motion of the system. Yes?
What is C1 in the diagram?
C1 is this constant length of the chord that's around the pulley. Sorry. So that's, any questions? Please pull up set 6. I also have a few copies of that here. Set 6, problem 2. So set 6, problem 2 is a pulley system, and let us write the chord equation for that system. This is my chord traced in yellow, and this is my mass A and my mass B. I want to find the chord equation. What do I do? First, I need to take a datum. Any suggestions for what the datum could be? Yes?
Did you go through this line at the top of this?
Exactly, I can do this. And I can define the distances to each pulley, to each pulley like this. That would be SA. And that other distance here would be SP. So what is the length of the chord equal to? It's 1 SP plus what? How many SAs?
6.
Let us see. 1, 2, 3, 4, 5, 6 plus 6 SP. Correct? Raise your hand if you see that. The length of the chord is 1 SP plus 6 SA plus all the remaining lengths, like this and this and this and this, are what? Constants, plus constants. So I can differentiate this expression to get 0 is equal to S dot B plus 6 S dot A. So S dot B is minus 6 S dot A. For if S dot A goes up by 1 meter, what will happen to, or 1 centimeter, what happens to S dot B? If A goes up 1 centimeter, what happens to B? It'll go down 6. Okay? And S double dot A, S double dot B is equal to minus 6 S double dot A. So if I write the position vector, if I have an origin, say here, I have an origin here, and I can write the position vector RA and the position vector RB. RA, I can write that as, and let me take EX anyway. RA is some constant along EX plus along EY, it's going to be, or minus EY. Along EY, it's equal to SA plus some other constant C2, EY. Do we see that? The position vector from the origin, I took the origin here to be point A, is some, along EY, it's equal to some constant plus SA, constant plus SA, and plus some constant along EX. So I can express VA then as being equal to S dot A